on applications. The basic idea of self-force is the influence of an object's own field on its motion. So in this case, I'm interested in the influence of the gravitational field on an object's motion. This is a kind of fundamental interest, but there are also astrophysical motivations for studying this. The main motivation is these systems called extreme mass ratio inspirals. In these systems, you have a stellar mass compact object, like a neutron star or black hole, orbiting around a very massive or supermassive black hole at the center of a galaxy or globular cluster maybe. As this small object orbits around, it emits gravitational radiation, which causes it to lose energy and eventually to spiral into the much more massive black hole. It's expected that a few dozen of these events will be detectable in ELISA's lifetime, when ELISA flies, hopefully 20 years from now. If we can detect the waveforms, we can extract a lot of very, very precise information about strong field dynamics and the structure of the space-time near black holes. So MRIs really act as a precision probe that no other system can act like. But in order to extract all the information, we need a very precise model, very accurate model of the motion of the small body and how it relates to the emitted waveform. So to do that, we need gravitational self-force. There's also more motivation coming from other binary systems. So let me depict the parameter space of compact binaries like this, the mass ratio here, the orbital separation here. The self-force theory applies when the mass ratio is very large. When the orbital separation is very large, you have post-Newtonian theory applying. When the separation is small and the mass ratio is small, the only thing you can use is numerical relativity. Unless you use effective one-body theory, which in principle is supposed to cover the entire parameter space. Now, you have interfaces between the different theories and areas of mutual applicability. So you can use any one of these theories to assist or compare with other models. So for example, if you have an accurate self-force model, you can use it to establish benchmarks for the extreme mass ratio limit of numerical relativity or post-Newtonian theory. You can also use it to actually directly improve other models, so you can determine high-order post-Newtonian parameters, or you can calibrate effective one-body theory using self-force data. There's also the possibility of directly modeling intermediate mass ratio inspirals or even comparable mass binaries just using self-force. The evidence for this comes from the work of Alex Letiec and collaborators, who has shown that the self-force theory has a surprisingly large domain of validity. So it's valid over here where you wouldn't expect it to be valid. So it's possible to use self-force to directly model other binaries than MRIs. Now, before I get into the more mathematical foundations of the theory, let me quickly run through the basic picture you would get with a point particle approximation. So let me assume that I can model the smaller object of mass little m as a point particle moving along some world line. And by that I mean it has a stress energy that's a delta function on the world line. Let me write the total metric of the system as a background plus perturbation. So in the case of a binary system, the background is the metric of the larger black hole. The perturbation is created by the small mass. And let me look at a linearized approximation where I'm solving linearized Einstein equation for the perturbation, and on the right-hand side I have the point particle stress energy. Now, what does the solution to that look like? Let me look at the field at a point x, a little bit away from the world line. Part of the field there has propagated directly along a null cone from the point particle. However, you can also imagine a perturbation being produced in some point in the past history of the particle. It comes out, propagates through the space-time, it gets scattered off of the background curvature, and then comes up and reaches the same point x. Also, these null cones are not actually cones, they curve due to the curvature, and so you can have signals propagating from multiple different points along null cones to the same field point x. So altogether what this means is that you have the field at this point x depending on the entire past history of the particle, not just something local. and this is called a tail effect. So let me illustrate that with a schematic picture of an emery. You can imagine the particle emitting radiation here, comes out, gets scattered off of the large black hole, and hits the particle at a later point. Now, what does this have to do with self-force? It was shown by Mino Sasaki Tanaka and Quinn and Wald in 1996 that basically the non-local tail acts as a gravitational potential around the particle, and it exerts a force, now called the Misataka force, that's roughly speaking a gradient of the potential. So this picture isn't that nice because the tail isn't the solution to any particular field equation, so it doesn't have a really strong physical interpretation. Also, despite the appearances of this equation, it's not actually differentiable on the world line of the particle. It's just that it works out that this particular quantity is defined. So in 2003, there was a better interpretation proposed for this Misataka equation by Detweiler and Whiting. Rather than splitting into a direct piece and a tail piece, they split the linearized perturbation into what they call a singular field and a regular field. The singular field behaves as m over r, where r is distance from the particle plus corrections, and it can be interpreted as the local bound Coulomb field of the particle that moves along with the particle. Then the regular field is that tail I talked about plus some local terms, and the combination of this is actually a smooth solution to the vacuum Einstein equation. So it can really be thought more accurately as a ambient vacuum field around the particle, whereas the tail you can't quite interpret that way. And what they found is that this Misataka equation is actually completely equivalent to the motion being geodesic in an effective metric, which is the background plus this regular field. There's another physical way of thinking about this. If you look near the particle at the force lines produced by the field, the singular field is symmetric around the particle. The regular field is asymmetric. So basically the force lines of the singular field cancel out, they don't add up to any net force, whereas the force lines of the regular field do add up to a net force, and so they influence the motion of the particle. So that's kind of a whirlwind tour of what cell force is about. In the point particle case, the rest of the talk, I will move very far away from the point particle case, talk about the motion of a small extended object. I'll derive first order equations of motion, second order equations of motion. If I have time, I will talk about how to practically calculate the field produced by the small object globally. And at the very end of the day, I will show that starting here, you eventually return to the point particle picture, and you rigorously derive the point particle picture from something with an extended object. Okay, so let me start with the extended object. Let me return to the question I posed right at the beginning of the talk, which is, how does a body's gravitational field affect its own motion? So this is really what the cell force is all about. So let's consider some space-time here with the object of mass m moving through it. And let me consider the regime where this mass and the size of the object are much, much smaller than any external length scale. So I'll just denote all the external length scales with this curly r. So for example, in an emery, that external length scale is the mass of the large black hole. Now the first way you might think of approaching this problem is to not make any approximations. Just think of some material body, fully nonlinear Einstein equation, and try to derive equations of motion for that body. So this was pursued by Abe Hart, and he generalized the Detweiler-Whiting results by decomposing the full metric, the solution to the full nonlinear Einstein equations, into two pieces. A self-field, which is a generalization of the Detweiler-Whiting singular field, so it's kind of the bound field that moves along with the object, plus an effective metric. But this effective metric now is completely nonlinear. And he found that a material body moves as a test body in this effective metric. What I mean by a test body is that it's geodesic in the effective metric up to couplings of the body's multipole moments to the curvature of the effective metric. So the multipole moments in this case are defined as some integrals over the stress energy of the material body. Now this is extremely elegant work and beautiful results, but for the rest of the talk I will not be talking about any of this. The reason is that the work is very limited in what it can do. So it's restricted to material bodies because it's all based on integrals over the body's interior, so it doesn't apply to the motion of a black hole, and we are most often actually interested in the motion of a black hole. Also, the basic idea of the method is that it gives you the equation of motion in terms of a metric, but it doesn't give you any way to calculate that metric. You would still need to solve the nonlinear Einstein equations, which doesn't really help you because that's the hard part. So we need a means of actually solving the Einstein equations, not just having the equation of motion in terms of the metric. There's also a minor drawback, kind of an aesthetic drawback, which is that Hart's effective metric doesn't satisfy the vacuum Einstein equation, so it's not really a nice generalization of the Detweiler-Whiting decomposition. So for the rest of the talk, I won't be talking about the fully nonlinear case, I'll be talking about perturbation theory. I will treat my object as a source of a perturbation of some external background spacetime. So we'll take the exact metric, split it into a background, plus first order perturbation, second order perturbation, and so forth, where this epsilon just counts powers of the mass of the small object. I'm going to assume that the body is compact, so that as I take the limit of the mass going to 0, I also take the limit of this linear size of the object going to 0. And then in this limit, I want to seek some representation of the motion of the object in the external background metric. So I take this exact spacetime, I map it onto an external background, and I want to take this complicated structure here and reduce it to just some world line in the background. Now there are some challenges that you must face in applying ordinary perturbation theory to these kinds of systems. First, you have multiple time scales. So you imagine a binary system, you have the orbital period of the binary, which is basically the size of the large object. But then you have the time that the inspiral occurs on, which is a much, much larger time, 1 over the small mass. The reason for that is just that at any given instant, the rate of change of the energy of the binary is extremely small. It's proportional to the mass. So the time it takes for a complete inspiral to occur is 1 over that rate of change. So you need to capture effects both on the small scale and the long scale. You also have multiple length scales. So near the small object, you have the scale of the object's size, which is its mass. Everywhere else, you have the scale of the external universe, which in the case of a binary is the scale of the other object. There are also more kind of fundamental issues. So despite having started with a point particle picture, the point particle is not a valid source in the fully nonlinear Einstein equations or even any nonlinear orders. It's only valid in linear order. So we can't really use it as an approximation for the small object. We also have to think about how do we capture the bulk parameters of the object without worrying about the details of its internal composition. We don't want to get into the real mess of equations of state or anything like that. We just want to have some bulk parameters characterizing it. We also have a question of how do we best represent the small object's bulk motion, for example, the motion of its center of mass. And I will talk about 2 different ways to do that. So we'll talk about 2 approaches to perturbation theory for these systems. First, the first approach I'll call the Gralla-Wald approach. So let's look outside of the object, so we're out in the vacuum. And I'll just expand the exact metric as a power series in epsilon. So each of the coefficients here depends on coordinates, it does not depend on epsilon. I just plug this into the Einstein equation, again outside of the object, so I'm in vacuum. I just solve order by order in epsilon. So I have a linearized Einstein equation for H1, linear operator acting on H2, sourced by quadratic combinations of H1, and so forth. Despite the fact that I'm looking outside of the object, the motion will actually be determined just by solving this sequence of equations because the motion is determined by the Bianchi identity. Now if you're expanding the metric in a Taylor series, you're expanding everything that it depends on in a Taylor series.
I have a question about
Sure.
the motion is determined by Bianchi identity.
Yeah.
Does it happen for every type of point type or there is some?
There's
Well, I know it happens, for example, for ideal fluid. But
no, so it's determined. You get an equation of motion for any body, but there is there's information that you need to specify in order for that equation of motion to actually be a closed system. So for example, if you're defining the body with a bunch of multipole moments, the higher moments, the quadrupole and higher, are only determined once you say what the object is, and you need to specify evolution equations for that separately from the Bianchi identity. So one of the things you have to expand in a Taylor series, if you're expanding everything in a Taylor series, is the world line of the object. So if I have some world line that depends on proper time and epsilon, obviously it is going to depend on epsilon because the motion is going to be influenced by the mass of the object. And I expand this out, I have a 0th order world line plus corrections. The 0th order world line is basically the remnant of the body as I shrink it down to 0 size and mass. So in the very limit, all I'm left is a single curve. And the corrections are deviation vectors defined on that world line. So I have a 0th order world line, and then I have deviation vectors pointing away from it. And that's where the self-force comes into play, in finding evolution equations for these deviation vectors. So the problem with using this method of representing the motion is that over a long time scale, as the body drifts away from the 0th order world line, these corrections get really large. So for example, in an emery, eventually your object spirals all the way into the large black hole, and you're nowhere close to where you started. You're nowhere close to the initial geodesic that you were tangential to, for example. So this representation of motion, and also the expansion of the metric that relies on it, is only meaningful and accurate for short times. It's not accurate on the long time scales of an inspiral. So the second approach, I'll call the self-consistent approach. In this case, you don't expand the world line. Instead, you try to directly get an equation of motion for the world line that faithfully tracks the body's bulk motion. So I don't expand this in powers of epsilon. I just try to find an equation for the full thing. Now, to do that, I need to construct an asymptotic expansion of my metric that's suitable for not expanding the world line. The way I do this is I take this perturbation and I expand it in powers of epsilon, but each of the coefficients is allowed to be a functional of the unexpanded world line. So each of the coefficients is allowed to depend on epsilon. Then we need a practical way of finding those coefficients, or defining them and then finding them. The method I use is adopted from post-Newtonian and post-Minkowskian theory in the harmonic gauge. So first I look at the full nonlinear equations. So I don't yet expand my perturbation in powers of epsilon. And I separate the gravitational degrees of freedom away from the material degrees of freedom by imposing a gauge condition. So the gauge condition I'll impose here is the Lorentz gauge, which is that the covariant divergence of the trace reversed perturbation, and this perturbation is this here, it's the whole sum, that's equal to 0. And I'm defining the trace reverse and the divergence with respect to the background metric. So with this condition imposed, the linearized Einstein tensor becomes a wave operator, and the Einstein equation outside of the object becomes a weakly nonlinear wave equation. So I have a hyperbolic operator acting on my metric perturbation equal to nonlinear terms on the right. Now this can be solved no matter what world line the object is moving on, unlike the original Einstein equation. So I can just leave my world line arbitrary and expand this in a power series using this expansion, and then just solve order by order, and I get all those coefficients still as functionals of some arbitrary world line.
Can you explain a little bit on G mu?
This?
What is the right hand side?
Oh, so this is just this is the second order Einstein tensor, so it's the piece of the Einstein tensor that's quadratic in the perturbation. And then you'll have cubic pieces and quartic pieces and so forth.
It's the same derivation that you solved on the
Yeah. So you can't actually solve it until you substitute this. Well, you can formally solve it as an integral equation, but you're really basically just reducing a differential equation into an integral equation, so it doesn't help you. But you can solve it just order by order explicitly once you substitute this expansion. So then we have the metric perturbation as a functional of some arbitrary world line. Then I go back and make sure that my full perturbation satisfies this gauge condition. And that will determine the equation of motion for my world line, because this gauge condition becomes equivalent to imposing the Bianchi identity. Now, regardless of whether I use the Gralla-Wald approach or the self-consistent approach, in both cases, you proceed by using matched asymptotic expansions, and that's how you derive the equation of motion. So here I've got my old binary. Let me zoom in on a region around the small object. Once I'm close enough, I can actually identify 3 different regions. I have an inner region that is at distances from the object, basically the size of the object itself. Out here in the external universe, I'm at distances that are basically the size of the larger object, so the size of whatever external length scales are around. In between the 2 regions, I have this region called the buffer region. Now, this buffer region is at distances much, much larger than the object, so I'm fairly far away from the object, but is much, much smaller than the external length scales. And because it's much, much larger than the object, I can still treat the object as a source of a small perturbation of the external background of the large object. But because I'm at small distances relative to the external length scales, I'm close enough that I can extract information about the small object. The way I extract information about the object is by introducing a second expansion, which we'll call the inner expansion. This expansion is zooming in on that inner region right around the object. So here's the full space-time. Here in orange, I've got the buffer region, and I'm going to zoom in on the region contained inside the buffer region. The way I do that zooming is I use scaled coordinates, r tilde, which is the ordinary distance divided by epsilon, and I keep this scaled coordinate fixed as I take the limit of epsilon goes to 0. So what that means is I'm keeping the size of the object fixed and sending all other distances out towards infinity. Now when you take this limit, the background space-time that you get is the background of the small object itself if it were isolated, so if it were not interacting with the external universe at all. And in that space-time, the buffer region is getting sent out towards asymptotic infinity. So you can sit in the buffer region and you can define multipole moments from the form of the metric in the buffer region. You don't need to integrate over the body or anything like that. You just look far away, identify multipole moments from the form of the metric. And those multipole moments are all the information that you need. So how do you use this to identify the equation of motion for the small object? Let me look first at the Gralla-Wald definition. So one of the multipole moments we can define is the mass dipole moment of the metric. Remember that the mass dipole moment corresponds to the displacement of the center of mass from the origin of whatever coordinates you're looking at. So here's a schematic picture where you've got the 0th order world line. You've got a buffer region that's centered around that 0th order world line. So let's work in coordinates that are centered on that world line. So out here I'm at some distance r. And then calculate the mass dipole moment of the inner background space-time in those coordinates. So here's the object slowly moving away, or it might oscillate around, but generally it's going to be slowly moving away from your 0th order world line. The mass dipole moment is basically this distance multiplied by the small mass. So this actually acts as a definition of Z1, of the distance you've deviated away from the 0th order world line. Now in the self-consistent definition, I'll work in coordinates centered on the accelerated world line. So I'll have my coordinates like this. I'm looking at a point out here. And I calculate the mass dipole moment of the inner background in those coordinates. And then I want to make sure that the center of my coordinates agrees with the center of mass. What I mean by that is that in those coordinates, the mass dipole of the inner background has to vanish. So this tracks the object indefinitely. So this way you don't have deviations growing, you just keep moving along with where the center of mass is. Now you might wonder how this even makes sense if you have a black hole, because a black hole is space-like divergence inside it. So how do you identify a world line with its center of mass? Again, it comes from matched asymptotic expansions. So here's the full metric, or rather the full space-time. you have some identification map from there to the background spacetime, and you also have an identification map to that inner expansion, or the spacetime of the inner expansion. So the world line you're installing isn't in the full spacetime, it's in the background spacetime, the external background spacetime. And your coordinates are also defined in that spacetime. So you're out here, and in those coordinates, you look over here, and you define the mass dipole there, using this identification map. So that's how you define a world line here, even if you actually have a black hole in here, and this goes down into a space-like singularity. Now how do I use this whole setup in practice? I will quickly go through and sketch the results at first order and then at second order. So the basic idea is to solve the Einstein equation in the buffer region, and that's going to get us the equation of motion. So in coordinates centered on some world line gamma, which I'll eventually identify as the object's center of mass world line, I'm performing an expansion for small r of the external metric perturbation. Now naively, you might think you should allow all negative powers of r, because as you get closer to the object, the field gets bigger and bigger, or the object's field gets bigger and bigger. But you actually get a cutoff on what the most singular, or what the highest power of 1 over r is. And that comes from the assumption that you have this inner expansion. So the inner expansion we're assuming is well behaved, which means that you can't have negative powers of epsilon in the inner expansion. What that means is you can't have negative powers of epsilon when you rewrite things in terms of that scaled distance I talked about. So if you take your nth order perturbation in the outer expansion, epsilon n times hn, and you take a term like epsilon n over r to the n, and you rewrite that in terms of r tilde, the scaled distance, you end up with something that's independent of epsilon. But imagine trying to introduce one order higher, r to the n plus 1 down here. Then you'd end up with an epsilon downstairs, which means that in your inner expansion, you'd have a negative power of epsilon. And just by assumption, we don't have that because we're assuming there's a well-behaved inner expansion. So the most singular power, or rather the highest power of 1 over r is 1 over r to the n in the nth order perturbation. So the nth order perturbation has an expansion like this in powers of r, starting at 1 over r to the n. Now how do we use this to extract information about the small object? Well, as I mentioned, these terms are independent of epsilon. So where could they come from if I was looking at the inner expansion? The only place they can come from is the background, because that's the only thing that's independent of epsilon. So what that means is these terms that are 1 over r to the n have to be coming from an expansion of the 0th order background in the inner expansion. And if you're expanding some metric near asymptotic infinity, the powers of 1 over r to the n that you see are defined by multipole moments of the spacetime. So these terms that are coefficients of 1 over r to the n we're going to be able to identify things in those coefficients with the multipole moments of the object. Now if I go through this procedure, what do I find? Let me sketch the general form of it. So I put this expansion into the nth order wave equation. So that's the equation where I haven't yet imposed the gauge condition. I'm just writing down the relaxed Einstein equation. And I solve order by order in R. Let me also expand these coefficients, so this, and so forth, in spherical harmonics. Now if I just pick some world line, then the solution I get at all orders, so all orders in R and all orders in epsilon, is fully characterized by two sets of things. First, the multipole moments of the object, and I'm defining those multipole moments just from the form of the metric. These come from terms that are behaving as 1 over r to the L plus 1. Then you also have smooth solutions to the vacuum wave equation. These are coming from terms that behave as r to the L. So these two types of solutions will be familiar just from undergraduate electrodynamics, hopefully. Now everything else you get in the general solution to all orders in R and epsilon is just going to be made up of linear or nonlinear combinations of these two types of solutions. So it takes some doing to prove that that's the case, but it is the case. Now, I'm going to take the general solution and split it into two pieces, the self field and the regular field. So this is going back to Detweiler and Whiting and Hart, although I'm defining these fields and using quite different language. So my self field basically is going to gather up everything to do with the multipole moments. And I'm going to interpret it loosely as the bound field of the body, but it doesn't really matter how I interpret it. The regular field is going to be everything that's collecting up these smooth solutions to the vacuum wave equation. So this is behaving as free radiation. And at this stage, it's undetermined because I haven't yet imposed any global boundary conditions, like no incoming waves or anything like that. But once I impose those conditions, then that will determine what the value of these fields is. And so this is smooth because R to the L times YL is smooth, and once you construct everything to all orders, you find that every term is smooth. Whereas this, if you take the limit of R goes to 0, it's divergent. So more concretely, at first and second order, you get things like this. So first order, let me split my H1 into the self field, the regular field. The self field behaves as 1 over R, and everything in it is determined by the mass monopole M. And this M is actually equal to the ADM mass of the inner background spacetime. The regular field at this stage, because I haven't imposed any global boundary conditions, is some undetermined homogeneous solution that's smooth at R equals 0. Now once I impose the gauge condition, I get evolution equations. I get that the mass is constant in time, and I'm going to assume that my acceleration of the world line has some expansion in powers of epsilon, and I find the leading order acceleration is 0. So at leading order, I have the equations for a test mass. It's approximately moving on a geodesic of the background, and its mass is constant in time. At second order, again I have self field plus regular field. Now the self field is behaving as 1 over R squared rather than 1 over R, and it's defined by a correction to the monopole, the mass dipole moment, and the spin of the object. So once I impose the gauge condition again, I get evolution equations. I get that the spin is parallel propagated along the world line. So this is just the leading order spin. It's later, at higher orders, you'll have torques acting, but at leading order, it's parallel propagated. I get some equation for the mass monopole, which isn't that interesting. Most importantly, I get an equation for the mass dipole. And remember, that's how I'm going to be defining the motion. So here's what I call the master equation of motion, which is an equation for the acceleration of the mass dipole moment. There's a bunch of things appearing here. There's a geodesic deviation equation. So imagine even if you had no spin, no fields, geodesic world line, so the acceleration vanishes, still the mass dipole moment is going to accelerate relative to your world line just because of geodesic deviation. So the object is going to oscillate. Typically, it depends on the space-time, but typically it's going to oscillate around your geodesic. Then you have the first order term in the acceleration of whatever your world line is. Then you have something that is called the Matheson-Papapetru spin force. So that's the coupling of the object's spin to the curvature of the external background space-time. Then you have a force that's coming from the regular field, and this is what's usually called the self force. Now this master equation, I call it a master equation because it's valid no matter what choice of gamma I make. So here I've drawn a kind of a crazy world line because I can pick any world line I like. And this equation is going to hold. It's going to tell me how the mass dipole moment evolves relative to that chosen world line. Now the equation of motion you get depends on whether you're working in the self-consistent case or the Gralla-Wald case. So in the self-consistent case, I'm going to define the world line to be the world line of the object by setting that mass dipole to 0. So then I get an equation for the leading order piece of the acceleration. And if you ignore the spin term, you can actually rewrite this equation as the geodesic equation in the effective spacetime G plus HR. So this returns us to the Detweiler-Whiting interpretation of the Mises-Takwa results. I won't go into the details, but despite having defined my regular field in a very particular way, I can actually show order by order that it agrees exactly with the Detweiler-Whiting definition, even though they're defined quite differently. Or it seems as though they're defined quite differently. So that's the self-consistent case. If you're in the Gralla-Wald case, then the acceleration vanishes to all orders, because you don't have an expansion of the acceleration, you have an expansion of the world line. So as soon as you've determined that the leading order acceleration is 0, you've determined that at all orders it's 0. So in that case, you actually get an evolution equation for the mass dipole moment. And remember, the mass dipole moment, I'm going to be identifying with that term Z1 in the expansion of the world line. So there you get an evolution equation for Z1. That's at first order. Now let me talk about second order. You might wonder why even bother with second order. Seems like first order, you're already getting all the interesting physics there. So one motivation for studying second order is in modeling emeries. So as I said earlier, the inspiral occurs very slowly on something that gets called the radiation reaction time, which is basically 1 over your small mass. If you neglect second order self-force effects, then you have an error in your acceleration, which is of the order of your mass squared. So you integrate this twice to get the error in position, and it's going to be mass squared times time squared. So after a radiation reaction time, this is actually an error of order 1. So you've got a huge error. So you need to include the second order force in order to get an accurate model over an inspiral time. Also, the second order force will help us in directly modeling intermediate mass ratio binaries or comparable mass binaries. And it will fix terms in post-Newtonian theory and effective one-body theory that are quadratic in the small mass. Now there's a problem with, or a challenge with going to second order, and that is that we define the mass dipole moment as the dipole moment of the inner background spacetime. So at second order, we're going to be talking about the correction to that. So it's going to be the mass dipole moment of the first order perturbed inner expansion. But beyond leading order, the inner expansion generically actually turns out to be not asymptotically flat. So the solution that we use to get around that is to find a gauge in which through that order it is actually asymptotically flat. So the non-asymptotic flatness is just a consequence of a bad choice of coordinates, basically. So you find a gauge in which it is asymptotically flat and it's manifestly mass-centered on Z0 if you're working in a Gralla-Wald case, or Z if you're working in the self-consistent expansion. So then that's in a very particular gauge, or a particular class of gauges, and we then want to go to some practical gauge where it's practical to calculate the solution of the Einstein equation, and we'll define the position in other gauges by referring to the gauge transformation from the mass-centered gauge to the practical gauge. We first run through that in the Gralla-Wald case. So on the short timescales to the Gralla-Wald expansion makes sense. The position relative to your 0th order geodesic is pure gauge. So imagine in some gauge your object is deviating away from this world line. You can just perform a gauge transformation that moves it back onto the world line, and then you've got the world line, or then you've got the object right on your world line. So what you do in this case is you start in a gauge that's mass-centered on your 0th order world line. So you've got Z1 and Z2 equal to 0, so the corrections are 0. Then under a small coordinate transformation, the position transforms just like coordinates do. So if you perform a gauge transformation to some other gauge that's more practical, you'll have some deviation from that world line, and the deviation looks like this. The first order, it's just the gauge vector on the world line, or on the 0th order world line. The second order, it's the second order gauge vector plus quadratic pieces of the first order. And you can use this to get equations of motion for how these evolve. In the self-consistent case, we can't use the exact same idea because on the radiation reaction scale, the position relative to the background geodesic is not pure gauge because it grows large over time. So in this case, we start in a gauge that's mass-centered on the accelerating world line rather than the 0th order world line. And then we demand that when we transform to a practical gauge, we don't move the world line. We want to keep on talking about the same world line because we want to make sure that that's the world line that the object is centered on. So I impose a condition to ensure that's true. And so then I'm when I perform my gauge transformation to the practical gauge from the mass-centered gauge, I'm setting delta z to be exactly 0, so I'm still ensuring that my object is centered on the world line that I'm getting an equation of motion for. So the equation of motion you get in the Gralla-Wald case at second order is very ugly, so I won't bother writing it down. In the self-consistent case, you get a surprisingly simple formula. So basically it looks just like first order, except you've got this extra thing sitting here. And now HR, rather than just being the linear HR, is HR1 plus HR2. And you can rewrite this equation as the geodesic equation in the effective metric G plus HR once again. So here I'm neglecting the spin and quadrupole moments of the object for simplicity. It's yet to be, no one's yet done second order including spin and quadrupole. So recall that here G plus HR is a physical field in a loose sense, that it satisfies the vacuum Einstein equation. Also this other condition that it's causal on the world line. It depends only, when you evaluate it on the world line, or any of its derivatives on the world line, it only depends on the past history. So from the object's perspective sitting on the world line, it really seems as if it's just some field that's sitting around it. And so this can be called a generalized equivalence principle. No matter what the object is, it moves on a geodesic of some, roughly speaking, physical metric that it finds ambient around it. So this is an extension of the Detweiler-Whiting results to second order. Okay, so far I've only talked about calculations in the buffer region, but in practice we want to calculate waveforms at infinity. We want to calculate what that HR is in order to actually solve that equation of motion. So we need to calculate the field globally. The way we do that is by introducing an effective interior metric. So I don't actually care about the details of the object, I'm just going to black that out. And then in the region where that was, I'm going to take my my local form of the self field and the regular field, just as an analytical local expansion, and I'm going to carry that all the way down to r equals 0. So the self field becomes a singular field because I had powers of 1 over r, and so it becomes singular in the limit r goes to 0. But I'm making this replacement in a way that doesn't affect the metric at all outside of this small blacked out region, and it also doesn't affect the effective metric even inside that region. So my G plus HR is being unaffected by that. Now this gives us a practical way of finding the field by using something called a puncture scheme. So we take the local expansion for the singular field in powers of r, we truncate it at some finite order, then we define the residual field, which is the full field minus that puncture, and because the puncture is approximately equal to the singular field, the residual field is approximately equal to the regular field. And if you do this properly, the residual field on the world line is actually identically equal to the regular field, and you can make any number of its derivatives identically equal to the derivatives of the regular field. Once you go away from the world line, they start to be different. And this becomes practical because in this blacked out region, I can directly solve for the residual field. So here's a second order equation. Basically, I've just taken my puncture from the left, moved it over to the right. So I have an equation for the residual field, and each of these terms is separately singular, but the singularities cancel out by design. So I have a regular source on the right hand side. Then outside the blacked out region, I'll just solve the ordinary second order Einstein equation. And you just impose a change of variables across the boundary between the two regions. So what this tells us is that to calculate the effective metric in here, and to calculate the retarded metric, or whatever physical solution you want, in the region outside, all you need is that expansion of the self field, which now is turned into a singular field, that you found in the buffer region. Let me talk about that a little bit more. So here's basically the field as a function of distance. Here you've got some physical retarded field. You've defined a self field and a regular field in the buffer region and outside. Here I'm talking about a material body, so the field becomes finite inside the body. Then we replace that with the punctured version, where we just smoothly extend this across. That's the effective metric. And then the self field comes up into a divergent field. But you're not changing anything outside. Now, just as one side note, people who are not familiar with the field of self-force often think that it's a theory of point particles and involves some regularization of divergences, but actually there's no real regularization. Everything is finite at every step of the way. You start off with finite fields outside the object, and the only reason you introduce these singular fields is as a practical computational method. And even once you introduce those singular fields, you're never actually evaluating anything that's singular. So the regular field that you're calculating, you just are writing as the difference between two analytically known divergent fields. So you don't actually have something that is ill-defined and then you regularize it, you just have finite quantities all the way through. Now let me, before wrapping up, just mention how I do recover the point particle picture that I talked about right at the beginning. If you're sitting outside the object, what does the field look like? So recall that I had multipole moments, or terms that are defining multipole moments look like this, 1 over r to the l plus 1. These are appearing in the self field. Using basic distribution theory, you can show that these terms, so the fields that are made up of terms like this, not the entire nonlinear field, but just these fields, are identically equal to fields that are sourced by delta functions or derivatives of delta functions on the world line. So if you're sitting in the buffer region or further away, in some sense the body looks like a skeleton. It's just a point-like object equipped with multipole moments. So again, you can't actually use that as a source for the full nonlinear equations, but you can identify it as the source for certain pieces of the field. At linear order, you can identify that as the source of the entire field. You can show that at linear order, the retarded perturbation in the buffer region and outside is identical to one that is sourced by a point mass stress energy tensor with support on your world line. So we recover the point particle, and we've recovered the Misotaka equation. So all the early point particle results do hold true at linear order, although non-linear order, things get more complicated. Now let me briefly summarize in my last couple seconds. So the basic game that we're playing here is determining the motion of a small object. We use matched asymptotic expansions and a self-consistent expansion to overcome problems of multiple length scales and multiple time scales. What we find is that at least through second order, self-gravitating compact object moves as a test body in an effective geometry, G plus HR, that is a solution to the vacuum Einstein equations. And the self field that you calculate in the buffer region is the only analytical ingredient you need, well, basically the only analytical ingredient you need to calculate both the effective metric on the world line and the retarded metric everywhere else. The current status of practical implementations, or current status in general, is that for a spherical non-spinning body, or approximately spherical and approximately non-spinning, the analytical portion of the problem is now completely solved. We have everything we need. At first order, we have a huge wealth of numerical results, mostly due to my supervisor, Lior Barak, but also Detweiler and others. At second order, there's at least one numerical implementation underway, but we don't yet have any numerical results. For a more general body, so a body that has a leading order quadrupole moment, we'll also need some model for the evolution of the body's higher moments. And that's it. Thanks for your time.
Thanks very much, Adam. We will have time for 1 or 2 quick questions.
So in practice, what do you do with the scheme? Is it for, you put it on computers and then solve it equations?
You put it on the computers, yeah.
What is the result? How does it look like? It's being calculated like?
So mostly people have been not actually evolving the orbit. They pick a background geodesic, they calculate the field sourced by that, and they calculate the force created by that field. And they don't actually use that force to evolve the orbit. Although now there has been one implementation where you've evolved the orbit using the force. But mostly what you do instead of evolving the orbit with a force is calculate some gauge invariant quantities. So there's now a whole list of gauge invariant quantities that have been calculated, like the ISCO shift, or something that gets called Detweiler's redshift variable, which is basically ratio between two timescales. There's tidal moments induced by the effective metric. There's spin precession, so basically the torque that the effective metric induces on the spin of the object. So these are all things that are gauge invariant that have been calculated and then used to improve post-Newtonian theory or improve effective one-body theory and to compare to numerical relativity. So in the near future, we expect to actually start evolving orbits, calculating waveforms, and having templates for something like ELISA, but that's still a lot of work.
What is the difficulty in this waveforms?
So the difficulty is that, okay, there's two difficulties. One, to get anything that's useful for ELISA, we need to include second order results, and just solving the Einstein equation at second order proves to be extremely complicated, especially because you need to maintain accuracy over a long time scale. Also, most of these numerical results have been confined to a Schwarzschild background. To have any kind of useful templates, you need to have a Kerr background. That's the astrophysically relevant background. There are some calculations that have been done in Kerr, but not a lot. And so going to second order and going to Kerr are the two major obstacles right now.